Hello and welcome to this lecture on chemical process modeling and simulation. In the last lecture, we discussed about the conservation of transported quantities in chemical systems, and through that got an overview of the various conservation equations of overall mass, species, energy and momentum. Fundamental to this whole study on the conservation of transported quantities is the concept of a fluid and a fluid that is under flow. Now, so the first serious model that we are going to look at, which pervades a lot of modeling efforts in chemical engineering systems, is that of modeling of a flowing fluid. And in doing so, I would like to spend about a few minutes on discussing the different length scales at which fluids are traditionally modeled, and then present an introduction to the concept of continuum. If you look at a flowing fluid, the flowing fluid along with it transports the following quantities. So consider the flow of fluid through a series of units where it undergoes many processes. The following quantities are typically transported and conserved: overall mass, momentum, energy, species. And also, if you are looking at charged species, they are a subset really of species, right? And the charges are also transported and conserved. Now, if you look at the various length scales in which fluid flow is studied and modeled, there are at least three different length scales. One is a molecular level, a molecular length scale, which varies typically of the order of 1 nanometer to 1000 nanometer or a micron. Again, in this transport of mass, species, momentum, that's linear momentum, and angular momentum, energy, charges, all of these are studied. And at the molecular level, if you look at it, any of these quantities are transported or are basically transferred from one molecule to another molecule by virtue of collisions. These collisions are by nature random, but then there could be external driving forces that could make these collisions biased in a certain manner, preferential in a certain manner. This could be a directional preference. This could be a species preference, for example, a charge-based preference. Uh, so there could be many different kinds of preferences that could be embedded into this. If you look at individual examples, right? But then fundamentally, any of these quantities that get transferred from one molecule to another by virtue of collisions. And therefore, this molecular transport is governed by molecular structure and intermolecular forces, and therefore when you're modeling a fluid at the molecular level, you have to come up with a model for the molecular structure as well as a model for the various intermolecular interactions. And then to get the properties of the overall fluid as a whole, rather than what happens to individual molecules alone, so we will have to use the tools of statistical mechanics to sum up, to add up all the interactions together to sort of comment on the interactions, and therefore whatever transports that take place in the entire system under consideration. And this statistical mechanics is a fundamental piece in the puzzle. And then the other side is molecular thermodynamics, which gives some sort of picture of the various intermolecular interactions, and it gives these intermolecular interactions, and it gives the framework for integrating intermolecular interactions between a pair of molecules to a larger system of collection of molecules. and then eventually take it to some sort of a continuous level of analysis, the next length scale, so to speak, right? So these two are fundamental pieces in the puzzle: statistical mechanics and molecular thermodynamics. Therefore, often you will find that a master's level course in thermodynamics usually will either touch upon statistical thermodynamics or molecular thermodynamics, occasionally both, and then try and make connections to the macroscopic thermodynamics that you learn at the undergraduate level. So the resultant equations are reasonably straightforward. If you are going to, for example, transfer momentum, then there will be obviously conservation of momentum. Two molecules coming and colliding. So initially they have a certain momentum together, and then when they leave subsequent to a collision, they have a certain momentum together. And similarly with energy. And this is only when you are talking in terms of some sort of a collision that is physical collision. If the system is ideal, then the molecules don't know each other until they actually come into physical contact. They occupy the same space at the same time. But then when I have mentioned that these transport of various quantities happens through collisions, oftentimes the collisions are used in a very loose sense, in the sense that there is that need not at all be any physical contact between molecules, because the systems in reality is far from ideal, in the sense that the molecules can start sensing each other's presence much before they ever come to occupy the same space at the same time, which never actually happens. And therefore there are various intermolecular interactions that govern this so-called collisions, right? So from an ideal systems perspective, so for example, one could think of conservation of kinetic energy uh, in the event of a collision. Now on the other hand, if you look at a realistic system, then one would have to consider the potential energy of interactions as well, and therefore it is the total energy that is conserved at all times. So that is how the transport of energy, for instance, from one molecule to another, and thereby in the whole system, would happen. So the resultant equations, when averaged, are integrated over the molecular length scales, which is from 1 to 1000 nanometers, should result in conservation equations at the microscopic level at the next length scale. So the next length scale at which fluid flow may be studied is a microscopic length scale, which is typically of the order of 1 micron to say 1000 microns or 1 millimeter. Now again, we can look at transport of mass, species, momentum, angular momentum, energy, charges in this microscopic length scale. The averaged effects of intermolecular interactions, which arise from some sort of a Brownian motion fundamentally, which is then biased by way of various interactive potential energies of various interactions. All of these together, then the averaged effects of these start manifesting in the form of friction, thermal conduction, diffusion, electrical conduction in the microscopic level. Now we will see how this happens in some level of detail, especially the sort of bridge between the molecular level and the microscopic level. I might choose one of these, one of these three, particularly friction, thermal conduction, or diffusion, in one of the lectures, probably diffusion, to sort of explain how this bridging of this length scale happens, and then you start seeing the manifestation of a molecular transport mechanism in a microscopic scale. Now we can use, in this length scale, we can use the tool of continuum mechanics to determine how transport occurs. Now this, of course, the central piece in this central idea embedded in this approach to look at transport phenomena, transport processes at the microscopic length scale, is the concept of continuum. is the hypothesis of continuum, which we will take up very shortly in a few slides. But this is how this is the tool with which all the models in of a fluid at the microscopic level is undertaken. Now the resultant equations, which are basically the various conservation equations when averaged over the length scales in the microscopic domain, then should result in transport equations at the macroscopic level. Now what is the macroscopic level? The macroscopic level, again we can look at the transport of mass, species, momentum, angular momentum, energy and charges. The averaged microscopic velocities, energy carried or fluxes will be used to write overall material energy species balance for an equipment or for a unit or for a set of units in a flow sheet. Now this is the macroscopic picture. Now this is somewhat similar to the kind of energy balances and material balances that you would have written in a course like a process calculation, or even when you look at any of the transport based courses, fluid mechanics, mechanical operations, heat transfer, mass transfer. When you're looking at designs of various mass transfer equipment or a heat transfer equipment, the kind of energy balances and species balances and the momentum balances that you would have written would all be at this macroscopic level. So you are not per se interested in the spatial variations of, for example, velocities in a reactor or in a plug flow reactor. That's why you call it a plug flow reactor, right? You neglect the spatial variations, at least in the cross section, and also of course at steady state along the length, or in a tank, or for example on a distillation equilibrium tray tower, right? An equilibrium stage in a distillation column. So you are not interested in the velocity variations and all. You are quite content with using an average velocity of average flow rate of the liquid phase and the average flow rate of a gas phase, and that is good enough to do the design of that particular equilibrium stage, and that of how many such equilibrium stages would be needed to achieve a desired separation. So here you are basically looking at an average flow rate, and the average flow rate is obtained from integrating the velocity profile, which you would have obtained by considering from a continuum perspective how there is flow happening, there is momentum transport or species transport and energy transport that would be happening. So is the case, it's not just the flow rates, also the temperatures. You end up choosing an average temperature, you end up using an average pressure, you end up using an average composition. You don't consider the possibility of variations, and you definitely don't consider the possibility of fluctuations in those variations, which would come when you have to look at a discrete way of looking at material. When you are looking at a molecular perspective, there will be the average value that you measure will be fluctuating. So even if you have, for example, a velocity profile that is parabolic, for instance, which is what you have studied in a laminar flow kind of a system, in say some sort of system like a flow through a cylindrical pipe, you have a laminar flow. If you were to measure the velocity of a particular fluid in one of the layers, the value that you use in the Hagen-Poisson type equation, which gives the laminar flow, the parabolic velocity profile at a particular position, the actual at a molecular level, if you look at the velocities of those molecules, that velocity that you use in the Hagen-Poisson equation would only be an average, and there would be fluctuations around that average. So basically, when you go from a molecular perspective to microscopic perspective, you neglect all those fluctuations, and then when you go from microscopic perspective to a macroscopic perspective, you even neglect the variations themselves. You just have some average value, unless you have to consider a variation along a certain length or a certain dimension. For example, in a plug flow reactor, naturally the conversion will vary as you go along the length of the reactor. But even so, in a macroscopic system, you probably would be interested in the exit conversion at the blood flow reactor, not how the conversion is varying intermediately. You may have that expression, but you may only use it to calculate the exit conversion. So the resultant equations form the mathematical models here of units or operations or processes or flow sheets, and they may be used for design writing analysis of chemical engineering systems. Now this is what you have studied in fluid mechanics, in heat transfer, mass transfer, reaction engineering, and this is going to be largely the focus of this course in modeling and simulation. However, the first part of this course is going to be at the microscopic level, and then there will be some introduction that I will provide to a molecular level modeling of fluids. All right, and that is increasingly becoming important because as we end up developing newer and newer fluids, one, and as we end up changing our scales of operations, where we move to microfluidic devices, we move to nanoscale systems and whatnot. So the whole process now, if it doesn't operate at the macroscopic level itself, then your modeling is necessarily confined to a microscopic level, and maybe in some cases it is necessarily confined to a molecular level model, and therefore some introduction to both those will definitely be given in this course. In fact, as a prelude to developing models at the macroscopic level, we would first start with microscopic level, then take a step back into the molecular level, and then come back to the macroscopic level. Now, if you look at what are some of the key concepts in fluid flow modeling, there are certain key concepts that are true, that are valid across all the length scales. The first concept that is valid is that quantities are conserved, overall mass, number of moles of the entire system, or the individual species, and the momentum and the energy. These are quantities that get conserved. And the conservation laws are absolute by themselves. There are no approximations involved in the conservation of these quantities. And then constitutive laws are developed at different scales and utilized to capture the effect of various phenomena across length scales. For example, as I've mentioned here, Fourier's law of heat conduction, and these are all approximate models. All the constitutive laws are approximate models. However, under well-defined conditions, these are excellent approximations. Just because they are approximate doesn't mean they are invalid, right? So these constitutive laws are developed and utilized. This is one type of key idea in fluid flow. So if we are to look at some of the key concepts in fluid flow modeling at a molecular scale, what are the conservation equations like? These conservation equations are written to account for the discrete set of intermolecular interactions that are considered in the system. Here is a very simple visualization. Of course, this is in a macroscopic sense, however, of the kind of intermolecular interactions that could take place. So here the intermolecular interactions are created, of course, by some external source, though this may or may not be the case in terms of a system at a molecular level. Now, before proceeding further with what has come up, I would like to point out two things. In this particular picture, the balls, the steel balls or the metal balls that are in there are interacting with each other by virtue of actual physical collisions, and they don't recognize each other until they actually physically collide. But this is seldom the case in with real molecules. There is always some interaction, intermolecular interactions. These interactions are typically the form of secondary bonds, ranging from van der Waals interactions, some induced dipole type, induced quadrupole type interactions, to then permanent dipole based interactions, then stronger such interactions like hydrogen bonds, and then if there are ionic species that are present, and then ion dipole, ion induced dipole, and then ion ion interactions as well, right? So these are the kind of secondary bonding interactions that cause that create a certain potential energy of interactions. So each molecule, unlike in these balls, not only has a kinetic energy but also a potential energy, and in any form of interaction between molecules, it is not just the kinetic energy that is conserved but the total energy that is conserved. The kinetic energy, of course, would be due to the Brownian motion arising from the temperature or the average kinetic energy. So it's basically, it is measured as temperature, right? The average of the kinetic energy for the system could be related to temperature. However, it is the total energy that is conserved, and we will look at such model frameworks towards the end of, after looking at the various microscopic picture of models of fluids, right? So back to what is there on the slide. Now, when we are looking at such gas molecules vibrating in a container, I would like to pose a couple of questions which you should consider, which is not only restricting the interactions of the molecules amongst each other, but also with the boundaries or the walls of the container, right? So are the container walls rigid, impermeable, adiabatic? If they are adiabatic walls, then they do not permit exchange of thermal energy from between the molecules that are present inside the system and the wall, and therefore the outside. If they are impermeable, the walls do not allow for these molecules to move out of the walls, or some other molecules to come in through the walls. If the walls are rigid, then the volume is fixed, and therefore there is no scope for expansion contraction type of change of state of the system itself. And if all three are true, then the total energy and the total mass are constants at all times unless nuclear reactions occur. Of course, we are not focusing on nuclear reactions. Net momentum is conserved. Momentum exchange occurs through elastic collisions in this particular simple ideal gas kind of a system, and net energy is conserved. Energy exchange also occurs through elastic collisions. And if the gas is non-ideal, as I was mentioning, the collisions result in changes to both potential and kinetic energies and the momentum. And this will be discussed separately. At the molecular level, again, as I mentioned, conservation equations are written to account for the discrete set of intermolecular interactions concerned. Now, if the container walls are permeable and non-adiabatic, then transport of molecules and energy across boundaries have to be considered. And when we discuss the fluid flow models, or fluid models at least, in a molecular level, we will address how these will be modeled. And these are captured in the molecular level by writing intermolecular interactions between the transported molecules and the molecules comprising the boundary. So you have to first model the boundary, and then you have to have some sort of an exchange mechanism, and then there is some sort of an interaction between what is outside the boundary and what is inside the boundary. In statistical mechanics, each such boundary condition in terms of the nature of the boundary, permeable, impermeable, rigid and non-rigid, and adiabatic, non-adiabatic, all of these boundary conditions, each boundary condition corresponds to what are called different ensembles. Again, as I said, this will be discussed separately but fairly briefly. Now we come to the central idea of this lecture, because fluid flow modeling, at least largely in chemical engineering, chemical systems modeling, at least at the undergraduate level, and even in the industry, largely happens at the microscopic or macroscopic level, and that for that it is usually sufficient that a fluid may be modeled as a continuum, and therefore the continuum hypothesis forms the bedrock of all such fluid flow models. Consider a macroscopic system like a glass of water. Now, if you look at the glass of water in a macro or microscopic length scales, not a molecular length scale, the system may be considered as continuous. In other words, if you were to consider an infinitesimal part of that system, water, H2O, is continuously distributed and fills the entire region of space. In other words, the entire region of space in that infinitesimal volume also is occupied only by H2O and there is nothing else. And you don't have to consider anything other than H2O, right? And all the properties assigned to that system are continuous functions of space and time. I can shrink that volume to zero effectively, and even so, then I will still have a density. I will still have, say for example, a viscosity. I will still have a property like specific heat. I will still have a property like isothermal compressibility. All of these will be valid, and these will be densities, will be functions of temperature and pressure. They are not functions of system. It's not a function of system volume. And therefore, if my density at ambient conditions for water is 1 gram per cc or 1000 kilograms per meter cube, I mean, I don't need to have 1 meter cube of water for this estimate to be valid. This will be valid even for 1 cc or 1 ml. If I take 1 ml, it is going to weigh 1 gram. And then I go further down and I say 0.1 ml or 100 microliters, then it should weigh 0.1 gram. And so on and so forth, on and on as I reduce the size until I will no longer be able to say this, right? Now, so if you look at the various properties, as I was saying, density, viscosity, even temperature, pressure, temperature, pressure are average properties here. But when you look at a molecular length scales, then these properties are harder to define in a sense in this particular way. In a molecular length scale, the system has to be considered to contain discrete components. There is only so many H2O molecules, and I am not arranging all these molecules in some sort of a lattice structure in a liquid, like for example a simple cubic or a face-centered cubic, or which is a close-packed crystal structure, for example. And even such a crystal structure will occupy only 72% of the total volume. The remaining 28% will be void edge, and we don't consider any of that in continuous, right? So in a continuum approach, right? So properties are no longer continuous functions of space and time. So I have to literally count each molecules, how many molecules are there, and then depending on that I have to define properties. So I may be able to write average properties now, but I have to look at ways in which I can assign those average properties to the entire region considered, what sort of fluctuations exist from the average, because these are all discrete entities, discrete H2O molecules. Now, so how do I define a temperature? How do I define a pressure? How do I define a density, viscosity? None of this is very straightforward from the training that you may have received in looking at a system like this, a glass of water, from a macroscopic or a continuum perspective. Going further in continuum perspective, in macroscopic and microscopic length scales, matter, now here is where there is a formal definition of this, matter may be assumed to exist as a continuum. In other words, it can be further subdivided into infinitesimal elements, and the properties defined for the matter in the macroscopic length scale, such as density, concentration, viscosity, and so on, are also defined for each of the infinitesimal elements, and I can keep on doing it, right? I can take one infinitesimal element and divide it into further smaller elements, and the same thing would apply. What is the advantage of this continuum hypothesis? This assumption enables us to study that infinitesimal element to gain understanding of the properties of the macroscopic system. So that sort of is the advantage. So I need to focus my attention only on an infinitesimal element, look at what is happening in it, and then generalize that behavior for the entire macroscopic systems. So can I do this for any length scale? I mean, can I just keep on dividing, a macroscopic system into smaller and smaller and smaller and smaller systems? Will there be a limit where this assumption of continuum will break down? Yes, there is a limit. And we will consider this in a very crude, simple sense. So this typically is the limit where the assumption of continuum breaks down is typically of the order of nanometers to micron. I've put micron here, but it is of the order of nanometers to micron. Now this is defined by the magnitude of a dimensionless quantity, typically called as Knudsen number. Knudsen number is defined as it's a dimensionless quantity, so it's a ratio of two lengths in this case. The numerator is lambda, which is the mean free path of a molecule before it encounters another quote-unquote collision, and L is the characteristic length scale of the system. So how far will a molecule travel before it collides with another molecule, and is that of the same order of magnitude as the length scale of the system? What do I mean by this characteristic length scale of the system? Keep in mind we started with a glass of water, and then we started looking at smaller and smaller and smaller and smaller volumes. Each case I'm looking at some sort of a characteristic length scale, right? A glass of water has a certain length scale, and then I'm looking at progressively smaller length scales, right? And the characteristic length scale I define by L. Now we have to understand this, of course. Mean free path is a concept that is strictly defined only for gases, right? And the moment you have a condensed phase, the moment you have something like a solid, for example, mean free path makes no sense. The mean free path is defined in a classical sense for an electron, which is a conduction electron in a solid, but not for the atoms and molecules themselves, the ions themselves, for instance. So mean free path is the average distance traveled by a molecule before quote-unquote collision with another molecule in the system. Now this assumes, of course, there is this complete or near complete translational degree of freedom, which is what I meant when I said that the mean free path can be defined clearly only for gases, and therefore Knudsen number is really well defined only for gases, right? So smaller than Knudsen number, of course, you can think of it like this. If the length scale is much characteristic length scale is much larger than the mean free path, then you need not look at individual collisions. The molecule would probably have undergone a vastly large number of collisions, so to speak, before the characteristic length scale is reached, and therefore you are looking at some sort of an average behavior of that molecule and thereby all such molecules as well, right? So smaller the Knudsen number is, smaller lambda is compared to L, the more valid the continuum assumption becomes. Now typically if you look at it, the continuum hypothesis is said to be valid. There are different estimates, but most people seem to converge on this Knudsen number being less than 10 power minus 2, that is less than 0.01. So when you have that kind of magnitude of Knudsen number, then you no longer have to consider some sort of a discrete nature of the system. In other words, what we'll be looking at, let's look at the rightmost corner of this picture. Now on the red colored arrow, full continuous line, that sort of indicates an estimate of the sort of distance one molecule will have to travel to collide with the other molecule, assuming that the other molecule is stationary. That is one length scale. And then the system length scale is given by the dark blue dashed line with two arrows. Roughly this is 1/10, so to speak, probably actually less than that, but roughly around of the order of 0.1, right? Now on the other hand, when In other words, what I'm trying to say is, if one molecule were to go from one side to another side, another end of the whole system, then it probably would have encountered a maximum of 10 collisions, and you can look at it counting the number of molecules that are lined up in the diagonal, so to speak. Whereas now, when your Knudsen number is less than 0.01, typically the number of collisions that the molecule undergoes is of the order of 100 or more. And when 100 or more such collisions happen, then the behavior of the molecule may be considered as an average behavior. So the individual collisions will matter less and less. It's the average behavior that will start dominating. So this is the picture of a Knudsen number being less than 0.01. Now, if you look at a glass of water, Knudsen number is of the order of 10 power minus 18, which basically means, the continuum approximation is very well valid. Of course, I have to say that this analysis, this sort of an explanation, has to be taken with a pinch of salt, because Knudsen number is not well defined for liquids. So please do not take this as exact. This has been used to sort of illustrate the concept of continuum. So if you were to look at typical values of lambda, so that now then you can look at for what kind of length scales will for these systems continuum approximation will be typically valid. For water, now keep of course in mind that water being liquid, this mean free path is not very well defined, but this is of the order of 1 angstrom. And for air, we are looking at say 6 angstroms. And therefore, if you are looking at say water, then 100 times this is 100 angstroms or 0.1 nanometers. Now, right, so around that kind of length scale onwards, so 100 nanometers, 100 angstroms is my bad, 100 angstroms is 10 nanometers, right? So 100 angstroms would be 10 nanometers. So above that kind of length scale for a liquid, continuum approximation seems to be valid. And of course, we have to still take this with a pinch of salt, as I mentioned. It's probably safer to look at say of the order of microns onwards. Then you say that the continuum hypothesis is valid. Now there will always be, because all these are estimates, so there will always be some length scales where you maybe have to look at the system from both the molecular length perspective model, as well as you can look at it from a continuum perspective. The continuum approximation may not be good enough, and it may contain some erroneous information. And on the other hand, when you're trying to look at the system from a molecular perspective, the challenge may be that the number of molecules that you will have to consider in say 500 100 nanometers, or 200 nanometers or 300 nanometers of say by 200 by 200 by 200 of water would probably be so enormous that realistic simulations may not be feasible. So these are all very interesting challenges, and there are still modeling techniques that are being developed, and there are still, more importantly, techniques that are being developed to sort of take a molecular level information and then scale it up to a larger length scale information. Now, if you look at the conservation equations in the microscopic level, I will not spend much time on this because we actually had an entire lecture. The previous lecture was exclusively dedicated on this conservation equations in microscopic and macroscopic level. Now, of course, we have to account for different mechanisms of transport. There is bulk transport, there is molecular transport. These conservation equations may be studied by examining either fixed boundaries of the system. That is basically the sort of a shell balance. You fix a control volume, and then in that control volume you look at what happens. That is called an Eulerian approach. Or you can also look at it from a moving coordinate system, where you sit on a fluid particle and travel along with it as it transports through the system. This is called Lagrangian approach, or relative coordinate system. And this, we will have one lecture where we illustrate the relationship between these two. There is value in doing both. And then you write a conservation equation like. And at the macroscopic level, again, this is the conservation equations are written for entire equipment such as CSTR, double pipe beat exchanger, and so on and so forth. Typically, because the equipment is fixed, the Eulerian approach is utilized. Again, we write such conservation equations, which we discussed in the previous lecture. So that brings us to the end of this lecture. Thank you very much. Again, this is a heavy bit of a lecture. So I hope you are able to follow all the concepts that have been presented here. If not, I would urge you to go back and listen to this lecture a couple of times. If there are any questions, as always, I am available. Please feel free to post the questions in the comment section, or contact me. Thank you, and you have a wonderful day.